In case this video comes before you're familiar with feedback electromechanical systems, input and output signals, error signals, or PID controllers, then what follows next is a preview of what this first course in control systems hopes to achieve. This video is about servomotor position control. Exactly what that means will be discussed first. This is the mechanical unit. That's the servomotor axis. The goal is position control of this axis, the output shaft, which is connected to the servomotor through belts and pulleys. This block diagram shows the most significant components. That's the servomotor. That's the potentiometer that measures the position of the output shaft. The output signal in volts is the potentiometer voltage. The desired position in volts is a triangle or square wave reference signal. The error signal is the difference between these two. An error signal of 0 means that the desired position is equal to the output position. In other words, the output position will be following or tracking the input signal when the error signal is 0. The PID controller modifies or manipulates the error signal. This graph shows all four signals from the servomotor system. Input triangle signal is blue. Output response signal is yellow. This is what we want the system to do. This is what the system actually does. The difference between the input and output signals is the error signal. When the error signal is 0, input and output signals are the same. The control signal is created from the error signal by the PID controller. PID stands for P for proportional, I for integral, and D for derivative. The controller may have P and D components, but not integral. That controller is called a PD controller. The controller may have P and I components, but not derivative. That controller is called a PI controller. PD controller created these results. PID controller created these results. Note the steady state error is close to 0. P-only controller created these results. The error moves around more. Another P controller, but with less proportional gain, the error is larger. Another P controller, but with a step input reference signal. A PD controller with a step input reference signal. All of these results were from the same real hardware system. Computer simulations of these systems are also possible and also extremely valuable during the design phase especially. MATLAB's Simulink is one tool for simulating real systems. But an accurate simulation requires accurate models of all components. These models are frequently S-domain models. These are real responses using the PD controller. And these are simulated responses. Simulated responses compare favorably with the real responses. This is the Simulink simulation program that created the simulation responses. Favorable comparison implies that the model components must be accurate. That's the motor and amplifier transfer function. And that's the 32:1 gear ratio. It's the integrator that converts angular speed to position. And the potentiometer transfer function converts position from radians to volts. PID controller has a derivative component, proportional component, and an integral component. That's the triangle or square wave input signal generator. That's the summing junction that subtracts the output voltage from the input reference voltage and produces the error signal. That's the MATLAB error variable to be plotted. That's the MATLAB output position signal to be plotted.